I think that when I joined the league, there were maybe 10 students. So going from 10 to 500 is quite impressive. Most of the students have come the last years though. When we introduce the students, we have like a week boot camp, and we use this program that we call Robot, and it's on GitHub under, I don't know if this is big enough for you to see. Join the league/robot. That's the GitHub repository. It's an open source MIT license, so you can do whatever you want with it. It's cool if you can fork it and create pull requests. This program was started by one of the league teachers, David Dunn. Before he wrote this program, we were using a program that we called Tortoise. And Tortoise was inspired by Turtle Graphics, and Turtle Graphics was introduced a long time ago by a programming language called Logo, as far as I've managed to figure out. And it has this little turtle that moves around, and you can tell the turtle how to turn and how far to move. The problem with this Tortoise was that it was written in Java, and it was one static class, and so you would say Tortoise was capital T because it was a class method, and then you say dot move. And David didn't think this was very Java inspired. It was we have objects in Java. We should create a robot and say new robot, and then we make that robot move, and not use static methods for everything. So I'm going to give you examples of, here I have my IntelliJ voice. Yeah, okay. This license I have actually won in a raffle at, not here.
Not here?
Not here, but it's, I use it a lot. So in this repository we have the source repository, and I think you can open it in Eclipse as well, because we use Eclipse as Keith just mentioned. But then outside of the project, or adjacent to the project, I have all these examples that are also in the repository, but it's not put into the jar file that you need if you want to create a robot project. So the first example is what a student typically starts with. Forget about the public static void main string args, because that is a lot of gibberish for somebody who's just starting to code. But we have Rob, who is a new robot, and then we say Rob move and Rob turn. Semantics are very clear. There's not much not to understand. And then we can run this, and it brings up a window, and we see Rob moving, and each of those statements takes just as long to execute as it takes for the robot to execute that statement. So you're actually watching your program executing here. So they are synchronous methods. We don't need to explain that to the students, but I think it's pretty intuitive. So from there you can notice that we have the same pair of statements repeated 4 times. So we can go to and create a for loop. And we can also, let me go here. We can create a for loop. And we can also see that a robot can have properties, like one of the properties is the speed. And then the robot can also have a pen, so it can draw where it's moving, and we can tell the robot to put the pen down. And then you can run that. Same thing, but now it drew a square. And so this far a student has learned about loops, has learned about properties, has learned to instantiate a robot from something that we can call a blueprint. You saw in the classroom we had these blueprints from Star Trek. And the idea with the blueprints is like a class is a blueprint. And that's something we mentioned to the students. So then we can let the students play around with this, and they can set the pen width, they can set the random color, they can change the degrees to turn and to move and so on, and they can create nice shapes.
Spirograph.
And then they can go home and show mommy, daddy, look what I made. I'm programmed a robot to draw this picture. And that's very satisfying. I sometimes get caught in playing with this myself. And this is the latest when I was playing with this just a couple of days ago, what I came up with. At first it doesn't look like much. It's fun. Since David wrote this program, I've been playing quite a lot with it, and I have made changes, and I refactored, and I have done a bunch of things. And one of my things that I'm trying to promote is don't use robot only the very, very beginning of the career of a new student. You can use it to teach much more advanced concepts. So the next example, one of the things I did is to be able to add a keyboard adapter to the robot. I added this method, add keyboard adapter, and then a class keyboard adapter. And that's a new concept that we can teach. What is an adapter? It's like you attach your keyboard of your computer to that robot that you see on the screen via a cable or whatever. You can imagine what's happening here, and if you run it, see, nothing happens, but then I can move the keys and turn and go backwards and forward and so on. And since one of the things you can do is to put a background image, you can very easily develop a game where you have to move the robot to certain places and then collect points as you move to these little places by navigating with the keyboard. But the point here is that there are not many keys that the robot reacts to. So the students can extend the keyboard. And they can, for instance, let a lowercase m means robot miniaturize, that makes the robot small. And capital M to expand it again, U to drop the pen, and D to pull it up again. And then otherwise, you just let the super do this. And so in example 3, I've done two things here. First, I replaced a robot with something that I found on the internet, which I can do. And well, that's fun. They can look around and browse the internet and be a little bit creative. And then they can use their own extended keyboard adapter. So M for miniaturize, and I can still move around. The pen is dropped. I can turn and go backward. I can lift the pen up, move, and so on. So there's nothing limiting the students from just doing this. They can do whatever they would like to do. So robot is written such that it can run in, you can have one thread for each robot. So every statement, every instruction that you give to the robot is going to be executed synchronously. So if you have two robots, and you say to robot 1, move 100, and then you say to robot 2, move 100, robot 2 has to wait until robot 1 has finished moving before it can move. But then you can introduce threads, and that's what is next example. So this is more advanced. It uses, we're using inheritance here. We're extending robot, and we are creating a little helper. Well, first we have a constructor, and then we are adding a run method and a little helper method to draw a polygon. And finally we have the main methods that's going to create 3 robots: triangle, hexagon, and pentagon. And then use an executor to have these 3 robots running in parallel. Which one do you think will finish first?
So does it change each time you're running?
Well, I've plucked them here. You can see.
It's the same.
The same. Well, why is it the same? Well, the triangle has to go 3 times 100, which is 300. Hexagon has to go 6 times 50, which is 300. And pentagon has to move 5 times 60, which is 300 again. And they all have to do a total of 360-degree turn, so they're going to use exactly the same time. So, I don't know about you, but do you think you have to be good in math to be a good programmer?
No.
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 No. And I don't think so either. I think there's a lot of people who are saying, well, look, just look at me. I'm a top-notch programmer and I'm not any good at math. But I think that programming can often be the doorway, the entrance to understanding and appreciating mathematics, and make it a little bit more concrete and less like, can sometimes feel a little bit abstract. So in this thing here, it's a lot of lines, very simple code. But the most difficult ones are these 3 lines here. Because in all these examples, the robot has just started any place and drawn a nice star or a nice regular polygon. But here we want to center the polygon that the robot is drawing to the center of the screen. And so if I run this, so first it's marking where the center of the screen is, and now it's going to draw this star shape around it, and it's going to be centered around that mark. So once it's finished drawing this cross here, you have to calculate how much it has to turn and how far it has to go to get to this vertex, assuming that each of these lines are 200 long. There's a little bit of simple math, but it's not that difficult. There are 10 vertices, and the robot turns 3 times around the center. So now how much does it have to turn at each vertex? Anyone can tell it out from the top of their head?
36 degrees?
Hmm?
36 degrees?
No. So the robot is going to make 3 times 360 degrees, which is 1080. Divided by 10, that's 108 degrees at each vertex. Simple as that. So it's not very advanced trigonometry. It's just to think a little bit. Now, so we saw an example where there were multiple threads. This one is, but the threads were not communicating. In this example, the threads are going to start communicating. They're going to be two robots, and they're going to wait for each other and perform certain things together. So in this case, I call the two robots Vic and June. Vic is the founder that Keith presented before, and June was the first lead teacher at the league. And so since I wrote this quite a few years ago, it was Vic and June at that time. And I choreographed a nice little dance between them. So the dance has two movements. The two robots come in on the scene, and then Vic performs his first movement, whereas, I have to close this, whereas June just waits for Vic. Here, June waits for Vic. And then once Vic is done with the first movement, he signals that he's done, and then June does the first movement. And after she's done, she signals to Vic that she's done. And Vic has been waiting for June, so now Vic can start on the second movement, and so can June. So the first, Vic and June, they both perform the second movement at the same time. And then after the second movement, Vic stops and waits for June to do an extra little turn of 180 degrees. And then June says she's done, and then they both exit the scene. I'll show this in a second. That's Vic. Now they're done with the first movement, and they do the second movement together.
Should update it to Keith and Sarah.
Yeah, Keith and Sarah. Yeah. And so I want to teach the students how this works, and at least some of the male students, they have been doing Indian guys where they have this talking stick. It's a nice stick decorated with feathers and beads and things like that, and they sit in a ring on an Indian tribal council, and only the person who has the stick is allowed to talk. And so all others, they have to pay attention to the person who's talking, and they're not allowed to talk. And then if somebody else wants to talk, they have to ask for the stick by raising their hand, and the stick goes around. So the concept of a talking stick is very well known, or easy to understand for most of the students. And when we explain what's going on here, what does wait for June mean? It means I want the talking stick. And then when Vic is waiting for June, he will say, well, June is not done, and then he will go in a loop until June is done. But the first thing he does is he relinquishes this talking stick and says, I want it back eventually, I'm not done, but here's the talking stick. So now June can go ahead, she needs the talking stick to say when she's done. And so she says when she's done, and then she notifies Vic, and Vic, who is waiting here, is then grabs the talking stick, loops around, checks if June is done, and June is done, so then he exits the while loop and exits the whole wait for June.
Why did you use wait and the while and the boolean while loop?
The wait, oh yeah, because when you're done waiting, it might be that June is still not done. So you should, good practice is always to have the condition in a while loop. It's a standard way of doing this. From this you can create other examples, maybe 3 robots or make another little dance, but it explains how communication between threads, and that's pretty advanced type of programming. I'll skip that one. Yeah, so we've seen how we can extend a robot, but we often hear, well, you should favor aggregation over inheritance. What does that mean? And my robot extends robot. So here's an example with, if I look at my robot, it adds an extra method, draw polygon. Could I have done the same thing using aggregation? And so I have my driver, and you can think about aggregation as something that is not a robot, but the driver has a robot, and anything you tell the driver to do, the driver will just tell the robot to do exactly the same thing. So in this case, we don't have inheritance, and we have exactly the same code for drawing a polygon. The drawback is that we need all this extra code to get the driver to do exactly what the robot is doing. Anything you ask the driver to do, the driver will just delegate that to the robot. And you have to write code for this. It's possible that there is some annotations defined by somebody that will generate all this code. Let's go up to the top. So I have my driver, it implements the robot interface, it has a robot, and then it has to override all the methods of the interface, simply delegating them to robot. And at the very end, we add a new method. It's quite tedious. You can't say that Java really encouraging, favoring aggregation over inheritance. Same example in Kotlin. Kotlin has this by robot, and it will generate all that boilerplate code for you. So you can say Kotlin favors, or it lets you favor aggregation over inheritance more easily. But I have had students that have taken the Oracle exam, and they have asked me, what do you mean by favoring aggregation over inheritance? And I just brought up this example and said, oh yeah, I get it now. Yeah. Example 8 and 9. Question?
I was wondering, you brought up Kotlin, I was wondering if you're teaching Kotlin.
No, we're not teaching Kotlin. I just wanted to show it, you know.
How much easier it is.
How much easier it is.
That
Yeah.
could change.
But go back to the favor aggregation over inheritance. That would mean you like aggregation, but there's a lot of boilerplate that you would have to do.
Yeah.
So why is aggregation a favorite over inheritance then, which is a simple method?
Because inheritance, as somebody has pointed out, it breaks encapsulation. You have to know how the methods, particularly the public methods of the class that you are extending, are implemented. Because let's say my draw polygon calls one of the public methods, which is it's doing, for instance, move, and that move was implemented in a certain way, and I didn't know that, for instance, move would call another public method that I have overridden. Now I'm thinking I'm just using the normal move of my superclass, but I'm not. I'm calling the move of the class that I have, where I have overridden that method. So for that reason, it can sometimes lead to some unexpected bugs. Not in this case, but you have to be very careful when you open a class for extension. You have to document very carefully what happens when you extend the methods. The rule is often that you make your class final to avoid people from extending your class, or you make certain methods final. And the methods that you are allowed to extend, there should be clearly documented what that implies when you extend those methods. So when you do use aggregation, you don't have all those problems. Example number 10. This was just a fun example. You can maybe use it to when we have the raffle.
Just the random number generator?
Well, yes and no. It's a race between 10 robots here. So you can place your bet, you can take your tickets and place your bets on which robot's going to win. And see how it does. The reason I did this is I heard, that some of the students wanted to do this and didn't know quite how to do it, so I was challenged to do that.
Gamble in grade school.
Yes.
Betting on the ponies.
Okay. So in all the examples that you've seen so far, the robot, it turns. Negative is counterclockwise, positive is clockwise, or it can move and it can just move straight. So what about having the robot not necessarily move straight? And so one of the slides, there were these two girls that had done this community project and for the garden project that Keith showed. They were my students, and I thought that it would be fun to teach them a little bit of vector graphics, and and I thought that maybe as their community project they could extend robot with some letting the robot not necessarily move in a straight line, maybe moving along a quadratic or a cubic curve. But once they were done with their project, they were so fed up with vector graphics and they moved on and they took the Oracle exam instead. So let me just run this. Computer is very slow. It's something that's taking a lot of. Apple Wii. I mean, one know what Apple Wii is. Well, that was that. So here we have a quadratic curve, and then it's a cubic curve that goes like this. And the code for this is, we have a quad 2 and a cubic 2 that is used. And it also has a relative true, which says, are you using the the top left corner as the origin, or you're using the robot's current position as the origin when you interpret these numbers. So a quadratic curve has 3 control points. The first one is the robot's current position, and then you have 2 other control points. Cubic curve has 4 control points. The first one is the robot's current position, and then the 3 other ones. So play around with that. Then we have the next example. There's also a follow path. So you can give it a path iterator, which is how you describe a path in Java. And you can get a path iterator from any shape. So in this case, I've created an ellipse. The width and height is the same, so it's actually a circle, and it's centered inside the window. So I just say follow the shape of this ellipse, and the robot will do that.
This is null.
So putting all this together, now you have multiple threads, you have quadratic and cubic curves, you have shapes. I'm not going to go through the code for this one, but first one who guesses what these robots do, 13 of them, wins. Can tell you it's going to be something amazing. What are they doing? First one.
Spelling. Your
Amazing.
name. Amazing.
Robot.
Robots. Creating words. Letters. Very nice. Polish.
There. So I told you I was going to show you something amazing. If you look carefully here at the logo, it says amazing programmers. So, then
But there's more.
recursive functions. How do you teach that? I found out that a lot of students, they love recursion. Once they learn it, it's like, aha, I get it, and they want to use recursion for everything. And typical example is, well, write factorial with a recursive function, but factorial you can write with an iterative loop, so it doesn't make much sense to write factorial using recursion, other than for just explaining what recursive functions are. So I feel that it's much more interesting to have the robot draw a fractal, because fractals are recursive by nature. So in this example here we have a I'm going to draw the Sierpinski triangle. So I've defined a method here for the Sierpinski move, and if it's a level 0, it's just a normal move. But if it's higher, then it's going to be a set of moves. So if I do the Sierpinski move of level 1, these 3 moves that you see here are going to be Sierpinski moves of level 0, which are just going to be normal moves. So let me comment this out and just show. Level 1 Sierpinski move. Yeah, it's like a line with a little cup on top of it. So each of these horizontal moves is a Sierpinski move of level 0, Now I can make a little, have the robot draw a little cup on top of each of these. If each of these horizontal moves is a Sierpinski move of level 1, which means I have to make the outer Sierpinski move a Sierpinski move of level 2. And then you can continue this way and you can write a if you were going to program this with all the particular instructions to make the robot do all these moves, it's going to be very complicated, but using recursion it's very easy. What's missing is the envelope line that goes from here to the top and then down again. So that's the lines that I commented out. And I've done this to level 7. Level 7 doesn't make more sense to go into higher levels, because then the thickness of the line will cover up the holes and you don't see anything more detailed. So for those who know what the Sierpinski Triangle is, it looks something like this. It's just that you have to continue the recursion infinitely. It's one way you can teach about recursive functions in a way that is not trivial and still fairly easy, in my opinion. So those are all the different examples that you can use robot for, and that brings me to the end of my presentation.
Could you show the framework of robot? How many classes is robot?
Yeah, I can go a little bit through the... let me just close some windows here.
Got a lot of JVMs running, huh?
So when we go down to the code here, the main class is robot, of course. We have, the way it works is that there is a ticker that produces a tick every 20 milliseconds. And each robot has a blocking queue. And what the ticker does, it just puts a token onto that blocking queue. The size of that blocking queue, the capacity of that blocking queue is 1. And if the blocking queue is full, then the ticker will just offer. That means it's not going to block. It's just going to say, well, it was full, and it returns immediately. However, while the robot is executing, it will often go in a loop, and the blocking queue that I'm using is called leaky bucket, inspired by the way you control the traffic in a network. When you want to pace, you don't want users to be downloading too much or uploading too much, then they kind of restrict how much data you can transmit using so-called leaky buckets. So here we are pacing the robot by saying in each iteration the robot has to consume one of these tokens from that blocking queue. So then they will just block there and waiting for the next tick, and then they will execute a little bit more, and then they will block, and then will execute a little bit more. That keeps the robot from not executing too fast. And it also makes all the robots, when you have multiple robots and they're running each in their own thread, since they're all moving to the beat of the same ticker, they will all keep up. and move at the same pace. You saw that with this big June example. When they were moving together, they were moving in exactly the same, exactly the same pace.
How about the horse race though? Apparently had one that moved faster.
And the horse race, yeah, what I do is, in the loop, I adjust the speed up or down by 1 randomly, and the speed determines how much the robot advances during 1 tick. So that is random. So that's why some of the robots move faster than the other. So all the movement, if it's moved or quad 2 or cubic 2 or whatever it is, there's this equation where there's a variable t, and this equation determines the position of the robot. And during a tick, there's an increment, a delta t, that is computed. And the higher the speed, the bigger that delta t is. So the t goes from 0 to 1. Now if the segment that the robot has to move is very large, then the delta t is going to be smaller. So the delta t is inversely proportional to the size of the segment that the robot is going to move, and proportional to the speed, so it increases. So but otherwise it's just an equation that determines the position of the robot. And yeah, we have a class called robot image because, well, we can use, the robot can either be a PNG or a JPEG, but David, who started this, he created his own format that he called ROBI, R-O-B-I. It's not very efficient way, but we needed something to read and write those images. Robot interface is just the interface that robot implements. The robot window is one window for all the robots, so it's like a static robot window that is shared. One of the nice things I think with robot is that you don't need to know anything about graphics when you start with it. You don't need to know how to create a window, how to move an object in a window. That's something that they learn in level 3 or level 2. So that's the third step, starting by level 0, 1 and 2. So it really gives a flying start to some computer animations.
It's swing based, right?
It's all swing based, yeah.
Any other questions? Yeah,
The
please.
kids that, they can understand threading well enough and breaks and so on, and synchronize code at level 1, or?
No, not at level 1.
You're saying
It's level 0.
Graphics is at level 3.
Yes, I mean, the first time they see this is when they come to a week camp during their vacation, and they take a 2-hour class every day of that week or something like that. I think it's 2 hours, 3 hours, something like that. And then they're introduced to this, and they learn like what I showed you in the couple of 2 first examples. They make a nice star and then maybe a for loop. That's what they learn during that week. But then when they are, I think threading comes up in level 5.
Yeah.
Yeah. Threading comes up in level 5.
So not all the examples are taught before you teach the graphics?
No.
Okay.
You can put it away, and then you can take and start later on. I've tried to promote this with the teachers. I don't think it's used that much at the higher level. I know that they have like a threading exercise using this at level 5, but that's about what I know about it. Yes?
What was the name of the turtle thing that this was based off of again?
Well, the program that we were using before was called Tortoise, but there are a lot of, if you look up turtle graphics, you'll see that Python has some turtle graphics. There are several different turtle graphics written for Java. So it's across many languages that you have turtle graphics.
Stanford uses something similar to this, I think. It's a graphic, it's a GUI that's got a robot that moves around and they do a move and a turn and stuff, and that's what they use in their intro level
Yeah.
computer classes program.
Yeah.
How do we contribute to the repository?
Well, the repository, I showed you the repository at the very beginning. Bring it up again. So it's on GitHub, join the league, and it's just to fork it and submit pull requests.
So this is the main class of robot, the framework, or is it the instructional level aspect? Or is it both?
This repository shows like what I showed you in my IntelliJ.
Okay.
Yeah, it's just the framework and the examples, like
Yeah.
it doesn't have the structure, all the recipes.
So if I wanted to, well, can you put a starry background to the drawing pad that the robots, the window that the robots are operating?
You can, I think, yes. I haven't done that but I think you can, yes. There's a Java doc. There's a Java doc generated, and in the robot interface, I put extensive comments, documentation, so that the jar, if you install the jar or you import the jar into your project, you will also get the source code and the docs. And so you can hover over any method and bring up the documentation for that method. Or any class. Everything is fairly well documented. And I think that's also important to teach the students, is to read the documentation.
You have to read?
No, it's cool to see kids getting excited about it. I mean, we just started a new batch of students at Wilson, and one of the kids is like, he must have done some programming before, I don't know, but he's like super excited about the robot stuff, and like he's like, did I do the spiral right? Like it's cute to see. And these are like, I think they're handpicked to be like people who don't have maybe these opportunities on their day-to-day. They may be at one of the schools that don't have computer science or whatever. So it's kind of cool.
Any other questions? Cool. Thanks, Eric.
My 5 years on